Adrian, who was away, the law of conservation of energy says energy's got to come from somewhere, go somewhere. It says the amount of energy you start with equals the amount of energy you end with unless you have an outside energy source. And a great example of a closed system, roller coasters. So Matteo, I was picking on you. It says this: suppose a 320 kilogram roller coaster below is at rest at the top of the first hill. It's given a very gentle push. In fact, let's assume it starts out at 0, okay? And it starts to roll. Matteo, I'm going to show you 2 ways to do these. We can do these numerically, or we can do these algebraically. This is about as long as algebra as I'm willing to go. So I'll show it to you, but I'll also understand if you want to just solve by plugging in numbers and get the thing by itself. Here's what I want you to notice. What does it want me to find in part A, Matteo? Yeah. Is there a change in height? Yes. Is there a change in speed? Yes. Is there a yucky, curvy path? This is definitely a job for conservation of energy. I'm going to write a little I here and a little F here. You can write that if you want to, but later on, final is going to be somewhere else, but this is okay. What do I mean by conservation of energy? Matteo, I'm going to start out by writing KE initial plus PE initial equals KE final plus PE final. The amount of energy you have because you're moving plus the amount of energy you have stored because of your height has to equal the later on amount of energy you have because you're moving because of your height. Is that okay so far? Then I always pause and I always ask, are any of these 0? Now for kinetic energy, what I'm really saying is, am I ever at rest? Matteo, am I ever at rest? When? Initial or final? So I can go, yay. Then I'm going to ask, is my potential energy ever 0? What I'm really asking is, am I ever on the ground? Yeah? Which one? When? Yes. This one I'm going to do algebraically because it's going to end up being pretty clean. Later on, we'll do some numerically. The equation for potential energy, Matteo, I believe was mgh. So that's going to be mgh initial. And that equals a half mv final squared. Matteo, have you been on a roller coaster before? Cool. Matteo, can you look at this? On the left-hand side, is there an m in everything? Yeah? Is there an m in every single thing on the right-hand side? In other words, is there an m in every single grouped term? You know what that means, folks? What happens to the mass? They actually cancel. So this is something you may never have thought of, but Matteo, you've been on a roller coaster? Before you got on the roller coaster, did they make you step on a scale so they could carefully balance out all the masses? Did they make sure that heavy people sat next to light people? Or, you know what? Could an empty roller coaster make it through the track the same way as a full roller coaster can make it through the track? Yes. Why? Because the masses cancel. I don't know if you ever wondered why you didn't have to step on a scale before you got on a ride, but there it is. What did you say I'm trying to find? Yeah. I want to get this thing by itself. I'm going to treat this 1/2 like a 1 on the top and a divided by 2. Timesing by 1 would mean I would divide by 1. Is that going to change anything? No. Dividing by 2 means I'm going to times by 2 over on this side. So I think what I'm going to get is times by 2 and then a G and an H initial. That equals VF squared. VF what? VF squared. Hey, how to get rid of a squared? So we're solving this one algebraically. V final is going to be the square root of 2 times 9.8 times, what's H initial?
90.
How fast are we going to be going at the bottom of the first hill? I actually think this works out evenly, quite amazingly. No yawning, Liam. I saw that. Not allowed. You get 42? If I multiply that by 3.6, this is going about 150 clicks. This is a good roller coaster. This would get your attention. This would be a world-class coaster. Not the fastest in the world. Some of them actually crack 100 miles per hour, which is about 50 meters per second, maybe a bit more. But this is close. 42 meters per second is getting close. Woohoo! Is that okay? Let's get a little more complicated. B says, how fast will it be going at location B? You know what, folks? I'm going to do this. Scribble, scribble, scribble. That's my final now for part B. Initial is still top of the hill. Is that okay, Candace? Cassidy, I've been doing so good, and then I went and botched it. Tired. Cassidy, is that okay? Yeah? Hey, Cassidy, is there a change in height between here and here? Is there a change in speed between here and here? Is there a yucky, curvy path? You know what I'm going to use to solve this? I think the law of conservation of energy. G. I'm going to go like this. KE initial plus PE initial equals KE final plus PE final. Is that okay, Cassidy? Are any of these zero? Are we ever at rest? Are we just do kinetic first? Are we ever at rest? KE final, we come to a stop at the top right here. What am they asking me to find in part B? How fast I'm going right there. I don't think the answer is going to be zero. Also, I think that would be a badly designed roller coaster if you didn't make it over the next hill. Is that okay? So here's my question again. Is there ever a time when the kinetic is zero? Mateo's nodding. When? Oh, I did say I think starting at rest. Is that okay? So can we go like this? Is there ever a time where the potential energy is zero when I'm on the ground? You know what? I don't think so. I think at the top and here, I'm not on the ground. Is that okay? All right. Well, mgh initial equals a half mv final squared plus mgh final. Candace, I did it again. Wow. Am I tired or what? This is going out on YouTube too. I'm the idiot teacher that can't remember my students' names. Wow. Cassidy, is there an M in everything here? Is there an M in everything here? Is there an M in everything here? Is there a brain up in here? No, I'm not getting your name right. Is there an M in everything? Have you been on a roller coaster? Did they ask you to step on a scale before you got on the roller coaster? You know why? Okay. By the way, in real life, don't write this down. In real life, there is actually some heat and the mass doesn't cancel. But if we grease the roller coaster down, we can get the heat close enough to zero that for all intents and purposes, Tori, the mass cancels and an empty coaster can make it through as well as a full coaster. There's a bit of a fudge factor there, so I'm simplifying things a little bit. But we're ignoring heat. We're in our magic physics world where everything works nice. Hey, what are we trying to find? VF? That right there? How? So that'll drop down like a domino, minus GH final, and that'll give me, you know what? I'll probably decimalize it, 0.5 VF squared. How would I get the VF by itself? Could either times by 2, or if we're lazy, we can just divide by 0.5. It's bad math manners to have a fraction inside of a decimal, but that's okay. How to get rid of a squared? Square root. Okay. This is one you all might want to try on your calculator because this is a fraction, a big fraction. Is there more than one thing on the top? Brackets. Is there more than one thing on the bottom? So it's going to be big square root of G, 9.8. Mr. Dewick, do the G's cancel? Is there a G in this term here? Is there a G in this term here? So G's don't, there's one here and the one here, but not there. It doesn't cancel. Gravity doesn't vanish. Be kind of a weird world if it did. H, and what was the initial height? I've scrolled down. 90, was it? Was it?
Yeah.
And then minus 9.8. What's the final height at location B? 50? All over 0.5. So I'm going to go bracket 9.8 times 90 minus 9.8 times 50 divided by 0.5. Square root of that. And amazingly, I think this one's going to work out evenly too. It's because I stole this from the internet and somebody bothered to make it work out evenly. 28. Let's keep designing our ride. Let's suppose, Julie, on the next hill, the third hill, which I didn't bother putting in the picture, let's suppose we want the roller coaster to have a speed of 12 meters per second. How high should we build the hill? Ty, would this involve a change in height and a change in speed and a yucky curvy path? Well, you know what? This is a job for conservation of energy. Is that okay? Third hill would be over here somewhere. I don't know how high or how low, but I'll just imagine that it's there. Is that okay? Is anything zero? Are we ever at rest? Where? Oh, initial? I agree. So we start out with no kinetic energy? Are we ever on the ground? Are we on the ground at the top of the first hill? That's a silly question. No. Oh, and at the top of the third hill, they want us to find a height. I don't think the final height is zero. That would be kind of wishy-washy too. Pardon me? VF is zero? PE final is zero? You're telling me the final hill is on the ground? I don't think so. I don't think so, right? We're visualizing this, my friend. There's the third hill. Is that okay? Yeah. Yeah? Okay. Well, PE is MGH initial. Half MV final squared plus MGH final. Hey, Ty, is there an M in everything here? Is there an M in here? Is there an M in here? You know what happens to the masses? That's kind of convenient. Even though they told me the mass, they really didn't need to. What's he asking me to find? What's how high of the third hill? What variable is that in my current equation here? Which one? There's two H's. Yeah. I want to get that by itself. Eventually. First, I need to move that thing over. How? Here's your hint. What's right there? I'm going to subtract it over. Not square rooting, because I'm not trying to get the v by itself. Okay? I know there's a square. I don't care. I'm not dealing with a squared because I'm not trying to get rid of the squared. So no square root. I think it's going to look like this. The GH initial is going to drop down, and then there's going to be a minus. Ty, instead of a 1/2, I'm going to write a 0.5. V final squared. That equals GH final. And now, how did you tell me we're going to get the H final by itself? Yes. Is that a fraction? Is there more than one thing on the top? Better put the top in brackets. So now we're actually getting into ride design. If you want your guests to hit the third hill at 12 meters per second, how high are you going to build the hill? It's going to be 9.8 times 90 minus 0.5. I want the speed to be 12 squared divided by 9.8. 9.8 times 90 minus 0.5 times 12 squared divided by 9.8. 82.7, heck, let's even call it 83 meters high. Okay. Which kind of makes sense. You want them to lose almost all of the, because at the bottom of the first hill, they were going 42. You want them to lose almost all of that speed. Your third hill better be almost as high as the original, which it is. Is that okay, Adrian? Is that okay, Adrian? Thumbs up? Vaguely? It's a lot to throw at you because I know you were away. Okay. This is the law of conservation of energy. Oh, example 5. Another roller coaster. Cool. Cool. Lynn, what do they want me to find in part A? Speed, yeah. I like the fact that you said speed and not velocity because we are in Scalarville. Jilin, does it look like there's a change in height? Yeah? Does it look like there's going to be a change in speed? Yeah? Is there a yucky curvy path? This is a job for conservation of energy. That's how I'm going to solve this. I'm going to solve this, my friend, by going like this. KE initial plus PE initial equals KE final plus PE final. Where I think initial is going to be right here and final is going to be right there. Folks, are any of these 0? Are we ever at rest? When?
Not at rest.
Are we ever at rest?
No.
So is the kinetic energy ever 0?
No.
Nope. Max, am I starting at rest this time? No, the picture says I'm going 12 meters per second. Okay, so am I crossing out any KEs? Nope. What about potential energy? Am I ever on the ground? Yeah? When? This is going to be a half mv initial squared plus mgh initial equals a half mv final squared. Lynn, is there an m in this term? Is there an m in this term? Is there an m in this term? Huh. Even though they told me the mass, 245, and I would get the right answer if I kept the mass in, turns out unnecessary. It would end up canceling at the end. What am I trying to find here, folks? Divide by 0.5. And then how do I get rid of a squared, Ty? This time I'm going to square root because I'm trying to get the VF by itself. There is a cleaner way to get there, which I'll show you in Physics 12, but this works. I'm going to get VF equals 0.5. What was V initial? Was it 12, Max? What was V initial? Was it 12? Squared plus 9.8. What was the original height? Was it 18? Is that right? All divided by 0.5, and then square root of that answer. This is probably a good one for you to try on your calculator. A half v squared times 9.8 times 18 plus 9.8 times 18 divided by 0.5. Oh, 5 square root. Do you get 22.3? Anybody else? Yeah. Now, Jilun, that's how fast you'd be going if we ignore friction. What if you were standing at the bottom of the coaster with a radar gun, I have a radar gun, and you clocked it at 15 meters per second instead of 22.3, it has less kinetic energy. Where'd that extra energy go? Heat. Heat. B says, how much was lost to heat? Gilles, is there still a change in height? Say yes.
Yeah.
Is there still a change in speed?
Yeah.
Is there still a yucky curvy path?
Yeah.
So this is still a job for conservation of energy, but as soon as I start talking about friction or heat, I tweak my equation. I say this. KE initial plus PE initial equals KE final plus PE final plus some extra heat that we lost. Are any of these zero? Are we ever at rest?
Yeah.
Are we ever at rest?
No.
Nope. Are we ever on the ground? Gilles, how would I get the heat by itself? Divide or minus? Why minus? Because, right, plus, right? Okay, so I'm going to get this. The first two just drop down. You said minus that? That equals the heat. A half m v initial squared plus m g h initial minus a half m v final squared. Hey Nick, is there a v in this last term?
Yes.
Is there a v in this middle term? Sorry, let me try that again. Is there an m in this last term?
Yes.
Is there an m in this middle term?
Yes.
Is there an m in this first term?
Yes.
Is there an m in this heat? This time the masses don't cancel. And this is why we try and reduce heat. We want to reduce friction. This is why we grease the rides down, just because we'd like to get it in real life as close to canceling as we can. The smaller we can get friction, the smaller we can get heat, the closer it is to the masses cancel. If you ever watch an empty coaster, will make it through a roller coaster because they built a good safety margin in. Yeah, it's plug and chug now. It's going to be 0.5 m. What was the mass? 245. 12 squared. Was it 12?
Yeah.
Plus 245. 9.8. Height initial 18.
Yeah.
Minus 0.5 245 VF squared. Oh, 15, the question told me. How many joules did we lose to heat? Hang on, Mr. Duke, you're missing a term. That's wrong.
I think you missed the 8 and 9.8.
I missed the 8 and 9.8. Thank you, thank you, thank you. Is that better? 3,300? 33300? And heat is a form of energy. It's measured in joules. Okay. So for lesson 1, I'd already assigned number 1 and number 2. I said you could try them. You can certainly now try number 3. And you can try 4, 5, 6, and 7. But I'll give you some time to work on this a bit later. But let's jump to lesson 5 and try a couple more of these, if that's okay. And I call this a little more conservation of energy. Says this, a slingshot. Hey, I grew up with slingshots. Every time we went camping, my dad would always cut us a new slingshot from some tree branch somewhere, and the first night he'd always make us a slingshot for the camping trip. A slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. How much potential energy is stored in the slingshot? Is this potential energy going to be MGH? They didn't give me a height, they gave me a distance. How the heck can I find out how much potential energy is stored in this slingshot? Work. The potential energy is going to be the work that the person pulling does, which is going to be force times distance. It's going to be 70 newtons times 0.9 meters, centimeters divided by 100, 0.9 meters, which I think is going to be an even 63 joules. Double check me, but I'm pretty sure 7 times 9 is 63. B. Connor, what's B asking me to find? If there was a 35-gram mass, how fast will it leave the slingshot? This is a job for conservation of energy. I know there isn't really a change in height. There's definitely a change in speed. And there's an energy transformation going on. In fact, I can go to a simplified version. I think I can say this. All of the stored potential, the force times distance, ends up becoming kinetic. Really, it's very, very similar to my Nerf dart gun. All of the stored potential is going to turn into kinetic. Okay. It's going to turn into kinetic. People at YouTube, what's going on? Shot one of my students with a Nerf dart gun. Okay. Why is this wrong? The potential energy this time is not because of its energy due to the Earth, like height. The potential energy this time, I actually know. 63 joules. That equals a half m v final squared. Pardon me? Wouldn't it just be 63? The kinetic energy is 63. That's what I've just said. Yeah, and I've said the potential energy is 63, and that equals the kinetic energy. Yeah. How would I get the V by itself, Connor?
Divide the 1/2.
Do I care about the 1?
No.
I'm going to treat this as a 1 divided by 2. So dividing by 2 is the same as what on this side? So if I hear you correctly, finally, and I think I do, you're telling me it's going to be 2 times 63. What else?
Divided by m.
Divided by the mass, and that gives me V squared. Square root. So the speed is going to be 2 times 63. Hey, what's the mass? Don't say 35 because it's not. 0.035 square root. 2 times 63 divided by 0.035. 2 times 63, Mr. Duick. That didn't show up. There we go. Oh, this is going to work out evenly. Nice. Get an even 60 meters per second, which seems about right. I've seen slingshots. They go roughly 2/3 of a football field in a second. I can follow it. I put a dot to go to 2 sig figs, so I went 60 period. It's a habit. So, what are good examples of conservation of energy? Roller coasters, woohoo! Skiing, woohoo! I can even, if I, instead of going MGH for potential energy, go force times distance. Bow and arrow, slingshot, Nerf dart gun. What else? Rope swings. Tarzan. Went to go see the new Captain America movie yesterday, and they had a preview for Tarzan. One's coming out as well. Okay. Tarzan weighs 82 kilograms and can run at 8 meters per second. He runs along the ground and grabs a vine, swinging into the air. How high does he reach? And I wrote down here, Dulp. Okay. Here's Tarzan running. It's about as good as I'll ever draw.
Yeah, that's quality.
Was better than I thought it was going.
Don't raise your expectations ever. Here's the rope swing, hanging, and I guess he's going to be running this way, and he's going to grab the swing, and he's going to swing up. Michael, here's my argument. Will there be a change in height?
Yeah.
Will there be a change in speed?
Probably.
Will there be a yucky, curvy path?
Yes.
I think this is a job for conservation. Mm-hmm. Are any of these zero? Is he ever at rest? I'm talking kinetic right now, first of all.
Sorry.
Is he ever at rest?
No.
Well, here's what I'm imagining. Here's my rope swing. I think Tarzan's going to come running. He's going to grab it. If I want to know how high he can swing, what's his speed at the top of his swing for a split second? What's his final kinetic energy for a split second? Which one of these can I cross out? KE final. Is that okay, Michael?
Yep.
Not often you're wrong.
It's okay, but it is.
What about potential energy? Are any of these zero? Well, I had somebody last class say, Mr. Dewick, technically the ground is here. This isn't on the ground. I said, ooh. Here's one of the lovely things about energy. Because energy is a scalar, you can put ground level wherever you want. I'm going to put ground level right there. In fact, if I go back to the last lesson, Connor, turns out if I had wanted to, for our roller coaster, one here, for part B, I could have let this be ground level, and instead of the first hill being 90 meters high, I could have called the first hill 40 meters high. 90 minus 50. And trust me, you'll still get the right answer. Probably with a lot less work because you were able to get rid of something with a zero. So you can put zero wherever you want to, where it's most convenient. You can make that be ground level. So I'm going to put zero, ground level, at the bottom of the line. Which means, woohoo! Pardon me?
Wouldn't the final be zero then, not the initial?
No, because the final would be at the top of the swing, right?
Oh, I thought we were starting it with him running.
He is.
We are.
Running.
Well,
But really we're starting right when he grabs, right when he grabs.
That makes sense now.
Okay?
I thought you were running in the ground first.
yep.
Michael, what's the equation for kinetic energy?
Okay, for kinetic energy, it is a half mv.
So it would be V initial squared equals, I guess, mgh final. Hey, do the masses cancel here?
Looks like it.
They do. Now this is kind of strange, but on a rope swing, provided the rope itself is strong enough, not only could Tarzan swing here, but Tantor the elephant could also swing here. And if he was going at 8 meters per second, he'll swing to exactly the same height as Tarzan, provided the rope doesn't swing. Okay? Or if, I don't know if there's a good rope swing in the Pitt Meadows area growing up. Out in Hope, there was a great one over Kakawa Lake. You learn very quickly how high you swing has nothing to do with your mass. It's everything to do with how hard you pushed off your initial kinetic energy. What's this want me to find, Michael?
The final height
How would I get the final height by itself?
divide the gravity over.
So it's going to be the VI squared drops down like a domino, divide gravity. Oh, and then I did that trick where instead of writing a 1 on the top and a 2 on the bottom for 1/2, I said that's just the same as having a 2 on the bottom. I can ignore the 1. That's going to be final height. Okay, how high? 8 squared divided by 2 times 9.8 equals 3.3 meters. Eight meters per second is pretty fast. That's sprinting. So if you run and grab 3 meters, yeah, if you really sprinted fast and you grabbed the rope swing, you could almost get ceiling height. Not quite. You'd have to be in good shape. No, it's Tarzan. He's in good shape. You want another good example of energy transformations? Slap shots. Put your pencils down. We're going to come back to this, but we're going to skip down, skip down, skip down. Stop yawning, Julie. Skip down, skip down, skip down, skip down. Example 5. Example 5, a bouncing ball. A bouncing ball, Max, is a great example of the law of conservation of energy. When a ball is bouncing, at the top of the bounce, what type of energy does the ball have? In fact, I can even be more specific, MGH. As the ball hits the ground, what type of energy does the ball have right when it hits the ground? Yeah. But I've also noticed that if you just let a ball bounce on its own, it loses height on each bounce. Does this violate conservation of energy? We lose some energy to heat and sound. So no, this doesn't violate the law of conservation of energy. The energy did go somewhere. It didn't magically vanish. So here's the thought experiment. Is it possible to drop a ball and have it bounce higher than it was originally dropped? You want to vote? We'll pause the video. Finish. So your homework is finished from last day, but also you can probably try number 1, number 2, number 3 successfully, but finish the homework from last day. Hang on.